radio slow.
Hi guys, today we're going to test the Eventuri intake on the E92 M3. The E92 is a fantastic sports car, has a 4 litre V8 engine which revs to 8,300, which is very rare for a V8 to do. The stock airbox on this car is actually very good. We did try to develop an intake kit for this car around 2 years ago, but we weren't able to improve on it. Over the years we've managed to learn some new techniques which we've applied to this car. We've created the Eventuri intake on this car now, which makes an improvement over the stock airbox. So what we're going to do today is run the car standard, show you through the features of the stock airbox and why it's so good, and then show you the Eventuri kit, fit that, and then dyno the car again to show you what the difference is. So we've just dynoed the car. The first run it made 417, the next run it made 423, and the third run it made 425. We found that the E92 M3 on the dyno does do that because the car's not able to hit its ignition targets on the first run, so the ECU tries to hit the targets and it keeps pushing the ignition advance forward. So we've got our baseline now for this car. So this car is completely stock at the moment, and we'll put the Eventuri on and we'll see the difference that it makes.
So I'm going to talk about the airbox and explain how it performs and why we feel it's such a good design. So you've got two parts of the airbox, two main parts, the inlet tube and the main airbox itself. And the airbox has two feeds. The primary feed is down under the front headlamp and the secondary feed is behind the front grills. The reason why we call this one a secondary feed is because it restricts down quite a lot before the airbox just here, so the amount of air you're getting from this feed is quite minimal compared to the feed from under the headlamp. The airbox itself has an exit at the back which connects to the bonnet, so as you're driving, hot air is literally pulled away from the bonnet with cold air coming in from the front. The tube of the airbox has flex in it because obviously the engine moves and the airbox is rigid, so you've got two concertina portions of the tube. We'll look at that more in detail when we take the airbox off so you can see inside. Other than that, it's a very good design. It's got good volume inside the airbox and it's obviously sealed from the engine bay heat. So this is the stock intake tube which fits between the airbox and the manifold. So if you look at the filter first, you can see it has a rectangular shaped outlet, which isn't ideal because the inlet is circular. But anyway, so looking at the tube itself, this is where we felt we could make the most improvements. So the interface of the tube to the filter itself is this rigid plastic part. As you can see, although the opening is quite large, the actual transition from the filter to the actual inlet hole is this area, and this is a very sharp transition with a big surface area which isn't being effectively used. This isn't really good for airflow because you've got air trying to negotiate this sharp turn. We'll take this piece off. Okay. Now, the other thing to notice is the flexible part of the tube has a large wall right there. That wall is exposed to the downstream airflow. So as the air goes through the tube, it hits that face and creates further turbulence. You've also got the two concertina portions, the first one being there and the second one on the other side right there. This is important to let the tube flex, but it introduces multiple surfaces for the airflow to bounce off, which create more turbulence. The final consideration in this tube is the connection between the tube itself and the manifold. So you can see here, this is the connection with the manifold. This goes over the manifold, and then you've got this portion which sticks out. So effectively it's just this inner area which is being used. You've got this area here which is just not being used at all, and the airflow then again has to negotiate from this surface around the corner into the manifold. So it's not a perfect design, but it's been done for excess clearance. So with the airbox being as good as it is, we focus our efforts on the tube, which is where the restrictions lie. So after many iterations and optimizations, we finished up with this design right here. And we've put it side by side with the stock system so we can show you a direct comparison of the features. So starting with the connection to the manifold itself, we've got obviously the same shape, but this time there are no internal ridges or faces. So whereas in the stock system you had a big face here, in our tube it's straight through, and it's as smooth as possibly can be. It's a pre-preg carbon fibre tube. You can see the weave on the inside as well. There is no fiberglass used. The other thing to notice, whereas in the stock intake tube you've got the concertina effect, in our carbon tube there is no flex. Now, movement is important, so rather than have flex between the cone and the manifold, we decided to design our tube so that the entire tube itself moves within the airbox, which is why we've got this region of neoprene right here which sits halfway inside the airbox, and as the engine moves, the tube moves laterally. So this portion allows the tube to move, which allows us to then have a solid tube which is as smooth as possible, no ridges, no interfaces. Now if we look at the other side of the tube, the region which connects to the cone, whereas in the stock tube you've got a rectangular shape with a very sharp transition to the intake, on our tube we're using a circular inlet because our cone filter is circular. That inlet transitions very smoothly to the oval shape. So going from circle to oval is much less adverse in change of geometry. Again, no flex, inside of the tube is smooth, allowing for the airflow to remain laminar. So our tube, as you can see, transitions very smoothly from the filter area to the engine area. The other thing to notice on our tube is aesthetically we've put some effort into making it look nice, which is important. So where the silicon goes, around this area, we've got a raised ridge which covers the back of the silicon, so you don't actually see the back of the silicon face, which can be a bit unsightly. So once it's installed, it looks very neat. It looks like it's supposed to be there, and it functions in terms of airflow more efficiently than the stock tube. The final piece of our intake system is our cold air scoop, which is again carbon fibre pre-preg. The scoop sits under the headlamp in the primary feed to the airbox, and we'll explain why we made this when we install it into the car. With the improved airflow of the scoop in place, you also get increase of debris which impacts the filter directly, also water. To counteract this, we've developed a guard which comes pre-assembled with the filter. So it's a stainless steel guard, and it comes attached to the filter as shown here. This stops direct impact of debris and water onto the filter. It doesn't block the hole, so you still get an increase of airflow through the airbox. Just to make sure, we did do a before and after dyno run of the system with and without the guard, and there was no loss of performance. So the airflow remains higher through the airbox, which means that the temperature remains lower, but you protect the filter from debris and water. So with the intake installed, we can run through a few of the features. First of all, you can see the airbox with the lid removed. It's such a good design. It's a big volume. There's not much more volume you can take out of this engine bay, and obviously it's sealed by this water drain. Again, so we didn't redesign the airbox. There's actually no need. So we've just focused on the tube as mentioned. The cone filter we've used is the biggest we could have used for the given space. It has a double cone. The second cone you can't see is in the middle for maximum surface area. The tube again, you've got this portion which is covered in neoprene, which is where the airbox lid sits. So as the engine moves, the tube can move with the engine without breaking the seal, because the neoprene is a sponge, so it compresses. The breather connects in exactly the same position as a stock breather, and again the silicon, you cannot see the face of the silicon because of this raised edge on the carbon, which is just a nice aesthetic touch we've added to the tube. The final piece of our intake system is our cold air scoop. Now, the main air feed to the airbox is under the front headlamp, and looking more closely at this feed, you can see that there is a ridge which comes back on itself before the entry to the airbox, which is right here, this ridge. So if you visualize the airflow coming in, it actually comes up and hits this ridge before the entry to the airbox, which will cause some circulation in the duct area. Not ideal for optimal airflow, so we designed a scoop to simply fit over that duct and remove the ridge by curving up before the ridge. So it's a more direct feed. This is the scoop. The curve is nice and smooth, and it curves up to sit just before that ridge. So I'll put this in place. By the way, and it's also held in place by a strip of VHB tape. The scoop is very closely molded to the shape of the stock duct, so the fitment is very snug. Right, that's the scoop in place. You can see now that ridge has been eliminated, so the airflow is now able to go straight up there without any interference, and it ensures that the airbox gets a nice full volume of airflow as you're driving. So we've devised a simple experiment to illustrate the effectiveness of the scoop. We're using a leaf blower to give us the airflow, and we're using this wind meter to measure it. Measured in kilometers per hour, and we'll show you how it works. The leaf blower is positioned so the angle of the airflow is representative of how it would be on the road. We've also strapped this into position so it will not move between both tests before and after the scoop to minimize variables. We're just going to show you the wind speed coming from the leaf blower before it enters the duct. Okay, so we've got an average speed of that short test of around 90 kilometers per hour, and we now position this into the airbox so that the meter sits directly above the hole in the airbox, which is fed from that duct. Okay. So that's the phone and the meter into place. We'll now conduct the test before and after the scoop. So the test is now finished. We'll show you the summary results. Okay. The first test we did was without the scoop, and the average speed you can see here is 43 kilometers per hour. We then put the scoop in place, and the average speed here again you can see is now 62 kilometers per hour, which is approximately a 50% increase in speed coming through the airbox, which is a very significant increase, and it validates our theory that the bump in the stock duct does in fact restrict direct airflow coming through the airbox. With the scoop in place and a 50% increase in airflow, we have lower IATs because you have a higher speed going through the airbox.
So we're fitted the Eventuri and we're going to dyno the car again. I've got the diagnostics hooked up and I can see straight away that the inlet temperature is about 3 degrees lower. That's partly due to the fact that we're using carbon fibre in the tubing to the airbox, and secondly due to the scoop in the ducting area being more efficient at throwing up air through that part of the system. So it'll be interesting to see how we get on the dyno now. Always up to temperature, so we'll give it a run now and see what it does. So we've just finished dynoing the M3 with the Eventuri intake on there. So we've done about 4 runs, making sure that the intake temperature stabilized throughout all of the runs. We found that the intake temperature was about 1 or 2 degrees lower with the Eventuri than it was with the stock airbox. And as you can see on the 4th and final run, we managed a 434.9. Stock was 425, so that's a gain of around 9 horsepower and around 8 to 10 foot-pound in the mid-range. So that's a fairly decent gain from a normally aspirated car from just the intake change.
So we've had a good result on the dyno with a gain of 9 horsepower, which we expect on the road to be even better because you're not relying on the fan. Furthermore, this plays out our theory that there are restrictions in the stock tube which we smooth out with our system, allowing for more laminar flow to the manifold. The temperature difference we also logged with the intake has 2 degrees lower intake temperatures compared to the stock system. And finally, we measured higher airflow values with our Eventuri compared to the stock system. So all in, good result considering that the stock airbox is so well designed to begin with. For pricing and availability, please contact your Dyno dealer.